Hello, and welcome to the decay of an apple. This experiment, known as the apple decay experiment, was done back in January of this year. You could see the apple decaying on my YouTube channel. The question I had is that can we mathematically determine the decay rate based on observing the color changes of an apple? To do this, I wrote a Python imaging script using the API SciPy. I would encourage anyone interested in photography or just science, investigate the SciPy API. Now, the Python imaging script that I created was used to calculate the average red, blue, green values of a photo. This is assuming that each photo, nothing's changed except for the decaying of the apple. I import the operating system because I'm going to be using the OS lister to identify all of the images. There's over 4,400 images, and making these measurements by hand is significantly complicated. I use the file name as the file for each of the images, and what I do here is I look for JPG files. How that's done is I use the if statement, if file name minus 4 colon is equal to .jpg. So the last 4 characters have to be .jpg. You will notice that JPG is in capitals. That's because I was using a GoPro camera to take these images, and in doing so, GoPro uses capital JPG. Since I'm running this on a Linux operating system, capital J and the common or lowercase j are seen differently. From there, I print the file name and the average measurement for RBG to the file WR file, which is the apple.csv file. Once that is done, I then close the file and I print done. The processing of each of these images takes 1 second, so over 4,000 images is roughly 2 hours. So let us begin. I am opened up the RStudio using R version 3.4.4, someone to lean on. In this statistical analysis, I'm going to need the following libraries to be opened. The reader, to read the apple data. ggplot2, because I'm going to plot some statistical variances with it, and mgcv for the gamma functions. Now that I did that, I'm going to read the CSV file. What's important to note here is that I have defined the columns as double for the average blue, green, and red. The reason why I do that is because the values collected using the SciPy are not seen as doubles and more as text. I'm going to now run the program, and there are some warnings. There was some data that was corrupted during the there was some data corrupted during the analysis, and so we're going to lose a bit of data. But for the most part, it works out perfectly. I did do an average against the red, green, and blue, but it didn't work out very well for me. It's all floating around 80 to 90, and as a result of that, the data set doesn't really matter much. Anyways, I got time in 0, 1, 2, 3 minutes. I got the red value, the green value, and the blue value, the averages of those for each image. And from there, I am now going to, what I'm going to do is assign x to time, and instead of the y variable, I'm going to use R for red, B for blue, and G for green. If I plot x against R, I'm doing the main here as red band, x as time in minutes, and y as red. You'll see why later. The main reason being that I'm going to also plot blue and green, and we want to make sure that we're looking at the right graphs for that particular color band. What we could quickly see is at around 800 minutes, or 13.3 hours, we start to see a rise in the decay rate. Well, I call it the decay rate, but we see a change in color to about 1000 minutes, which is 16.7 hours after I cut the apple, and 25 hours, or 1500 minutes, we start to see it drop a bit. And that's in the red band. What does the blue band look like? The blue band sees a drop in color, and then it rises up again. But what's interesting here is that at about 800 minutes to 1500 minutes, we see this, which is consistent with the red. So we must be on to something. Let's look at the green band. Again, we see at about 800 to 1000 to 1500, we see a slope. It's much minor, but we still see a slope. We see some outliners in here, which is attributed to some of the color, and what we could probably conclude is that the green band, although it does show a increase in values, it's not really that significant when it comes to decaying of an apple. So let us proceed. If I take a data frame in the red, what do we see? So I'm going to take the data frame x comma r, and I'm going to treat it with a linear model, red as a function of x, and we'll do a summary and a plot. So let's look at the summary. What the summary tells me is that 56%, or 0.5639 is r squared, but 56% of data fits on the red model as a straight line. If I plot the model, I see that we have a linear increase and a linear decrease. This is the 56% that fits. Here, little bit here and most of it here. The theoretical quantities against the standardized is relatively flat. The scale locations are against the fitted values against the standardized residuals. It's relatively flat actually because it was 0 to 1.5. And we see that the data fits well within the range, and Cook's distance doesn't show up, so all this data is pretty well, it fits quite nicely. Let's look at the blue band and see where that fits. Again, 73% or 0.7322 on R squared. That's pretty good fit for the blue data. How does that look? Again, pretty well 0. As you can see that the fit here, and this is your 73% right here. Pretty well flat for a normal Q. Scale location, pretty well flat. And the residual versus leverage, again, it fits quite nicely. It's outside, it's all within the Cook's radius. And we got some guys up here. When you look at the residuals versus leverage, we see that all the data fits well within a good range. Cook's distance doesn't show up, which indicates that this data all fits nicely. We have some potential outliners here, 1 and 2. What this represents is that the data is fitting well. So let's look at the green. Plot that. Looking at the green band, we see that it's a 32% fit in data, 0.3207. Not very good. Didn't expect that from the plots. Again, but the residual versus fitted is basically 0. These are the outliners that are causing the 32% fit because they're so far out, but we could ignore these and we would see that it's pretty close to an 80% fit. Again, normal Q theoretical quantities against standardized residuals is almost 0, which is pretty impressive. We got these guys here that are our outliners that need to be dealt with. I'm not going to worry about that too much. The scale location is pretty well flat. Again, here's our outliners that are causing us some grief. 3919. We could delete these guys and probably clean up the place, but I'm not going to worry about it. Residual versus leverage is basically 0. Again, these guys are our outliners. We have to deal with those guys potentially. Now if we look at the gamma of red, we'll see, as I mentioned, red 56.4% is explained. That's basically what we were expecting. Blue will be much higher. Let me just do that. That's 73%. And of course we have our green. At 32%. So very similar results. What we can conclude though is that the data all represents, the red, blue, and green do represent themselves very well. a GG plot with the smoothing function for the red is here, and again we could see a well-defined at about 800 to 1500. The decay is significant. So again, suggesting that between 13 hours after cutting the apple to 25 hours, the decay rate is at its greatest rate. The other color observations, we'll look at blue, and blue shows the same thing. At about 800 to 1500, we have a maximum decay rate, and the blue would suggest that it still decays but at a lower rate, which is consistent with the previous observations. If we look at the green, we do see the same thing, from 800 to 1500 maximum decay rate, and you can see that it still continues to decay but at a much lower rate. So this is green, showing significant decay rate at 13 hours to 25 hours. At 1000 minutes, that's 16.7 hours. We see the same thing in the blue, and we see the same thing in the red. So what we can conclude from these three observations is that there is definitely a decay rate that increases at about 13 hours after cutting the apple to 25 hours after cutting the apple. We have the maximum decay rate of an apple. Well, I hope you enjoyed this experiment. I had a lot of fun doing it, and I just want to encourage you to continue experimenting. Don't be afraid to write the odd program. There's a lot of APIs out there in Python that people have already done for you, and just understanding how they're used, greatest challenge. But once you've done that, you can do some really interesting stuff with observation, programming, and some statistical analysis. Thank you for watching. Have a great day.